Alright, so this next little section, part of section 4.3, is an application of the second derivative. So we've already learned how to use the second derivative to determine concavity and points of inflection using the concavity test with a sign chart on the second derivative. So what we're going to look at here is, now going back, this is going to give you an alternative test for relative extrema. So instead of using our first derivative test, and if you will recall that on our first derivative test for relative extrema, you had to find the first derivative, find the critical values where the first derivative was either 0 or did not exist, but did not exist but was still a point on the original function, so f of the critical value did exist, and then you did a sign chart on the first derivative, and then you made a conclusion of everywhere that there was a point on the function f for which the derivative was 0 or does not exist, and the first derivative switched signs, then you got to conclude that you had a relative min or a max depending on which way the sign switched. This is going to give us an alternative for the first derivative test, and it's going to use the second derivative. Now I will comment that this is really useful mostly when the second derivative is easy to find. We obviously don't want to do a lot of extra work to find a second derivative when we could have done a first derivative test. Alright, so, but then there will also be problems. You can't just not learn this one because there will be problems. Remember, we hit everything using the rule of 4. So either graphically, numerically, algebraically, or verbally, there may be things where you don't actually have a formula, but maybe you're given information about the second derivative either verbally or through a graph, and that you have to use the second derivative in order to make conclusions about relative extrema. Alright, so what we're going to do is we're going to make sure we know that we're looking at a function where we have a critical value of f. Now remember that a critical value of f is where the first derivative equals 0. So we're not talking about finding the second derivative and getting where the second derivative equals 0. Those are possible points of inflection. This is going back to, we're looking for a critical value of f, which is a candidate for a relative extrema. And we're specifically only looking at the ones where the derivative is equal to 0. Notice that this then tells us that this does not work for cusps, because the first derivative would not exist for a cusp. So we're only talking about the smooth relative extrema, where you have your hills and your valleys like this. Okay? So we have to have a derivative there, and that derivative has to equal 0. So we're looking only at those critical values. And then the second part of this is if the second derivative exists on an open interval containing that, okay, then we're going to be able to use the second derivative to determine whether we have a max or a min. And the idea here is that what you know is that when the second derivative is positive, your original function is concave up, which would mean that if you had a smooth curve and you had an open interval for which it was concave up, and you plug the critical value in that had a slope of 0, and it's concave up, it has to be a relative minimum. That's the only choice. Notice I don't have to do a sign chart here. All I have to do is, if I have the second derivative, is plug the value of c in, and if it's positive, then I know it's a relative min. And then if it's negative, then we would know that it's this scenario, and it's a relative max. So it basically gives us a quicker way than having to do an entire sign chart. We can do just a quick test. Now, of course, there is this caveat down here that if your second derivative equals 0, the test fails and you have to go back to the first derivative test. So that's an unfortunate, but if the second derivative was easy to find, all you're doing is plugging in a number, and if the test fails, then you already have the first derivative, so you haven't done too much extra work, and a lot of times it does end up being a little easier. Alright, so let's take a look at example 4. I want to find the coordinates of the relative extrema, and I want to justify if possible using the second derivative test. Okay, I could do it with the first derivative test, and on the AP they don't care whether you use first derivative or second derivative justifications. I'm just going to do this one using the second derivative because it's really easy to find. So I find my first derivative. We also know that this is polynomial, so f is continuous and differentiable, so I don't have to worry about the cusp or anything like that. So we take our derivative, which is going to give me negative 15x to the fourth plus 15x squared. I immediately find my critical values from that first derivative. That would be where that first derivative equals 0. And that would be, I'm going to go ahead and factor while I'm there. Let's pull out a negative 15x squared, which would leave me with x squared minus 1. And so x would equal 0 or plus or minus 1. So see, pretty easy. Now if I was doing the first derivative test, I would now go do a sign chart for this. But what I'm going to do instead is I'm going to come over, instead of the sign chart, I'm going to find the second derivative because it's really easy to find. So we have negative 15 times 4, so negative 60x cubed plus 30x. And when I get to here, I am not going to do anything else. I'm not doing a sign chart or anything. What I know is that I'm going to take my critical values here, and I'm going to take them and I'm going to plug them in to the second derivative. If I plug in 0, I get 0. Unfortunately, second derivative test fails. We'll talk about what to do there. I plug it in for 1, and if I put 1 in, I get negative 60 plus 30, which is less than 0. Notice I don't even care what the value is. All right, which tells me that f is concave down at x equal to 1, which tells me that x equal to 1 is a relative max. Okay, and then our last one, we plug in negative 1. Negative 1 is going to be positive 60 plus negative 30, so that's going to be greater than 0. So f is concave up at x equal to negative 1. So x equal to negative 1 is a relative min. So in terms of finding the location, all right, now I'm going to come back because I have to kind of highlight here this. They like to mess you up on this part. I want to find the coordinates of the relative extrema. Right now I have the location of the relative extrema. I'm going to have to do one more step and find the coordinates. So I'm good. I'm done. And I have a justification. X is a relative max because the second derivative is negative and it's a critical value. Right? Now this one, unfortunately, our second derivative test failed. So we do have to do a sign chart, but I don't have to do the entire sign chart. I only have to do the sign chart close to 0, which means that you put your other critical values on there, 0 and 1, and I don't care about what's over here, I don't care about what's over here, I only care about the 2 either on either side of this. So if I plug in values in between, let's say negative 1/2 up here, negative 1/2 squared, I have to do a little bit of work here, f prime of negative 1/2 would be negative 15 times 1 over 2 to the 4th, which is 16, plus 15 times 1/4, and thinking about what's larger, obviously 15/4 is larger than 15/16, so this is going to end up being positive. And this is f prime. Okay. And then I am plugging in 1/2, and 1/2 would give me the same result. So it is positive. So it was increasing, f was increasing, and then increasing. So x equal to 0 is not a relative max or min. Okay, because the first derivative did not switch signs. And again, because they don't interpret my sign chart, I should say because f prime does not switch signs. And then let's just finish out the problem because they ask me to find the coordinates. So I need to plug them back into the original to get the coordinates for each. And so if I plug in 1, we get -3 plus 5 or 2. So 1, 2 is my relative max. If I plug -1 in, that's going to make it +3 minus 5, so that's -2. And there you go. We have our relative min, our relative max, and then we have our point where the test failed, and it could end up being an actual relative min or max, but in this case it ended up not being a relative min or max. And then I'm actually going to stop this video right here. That was a nice short one because I think this is fairly easy to understand, and then you're basically just going to need to practice this from now on, which is if you can find a easy second derivative, you can use the second derivative test for relative extrema instead of the first derivative test for relative extrema. And we'll just kind of practice this on the worksheet. The next video that I'm going to do is really kind of goes back to the idea of being able to look at a graph and using a graph that's given to you in order to answer questions. Okay, and in this next video what I'm going to do is I'm going to do 5 part 1, and I'll probably leave part 2 for you to do on your own. So I'm going to stop this video and take another break. This one was a short one, and we'll do example 5.